Good morning, friends. Hope all are doing good. So, today I am going to take session 3 of circular slabs. So, now we can see about the slabs which are fixed at edges. Hope everyone will be having your notes with you. Just we can see what are the equations for doing a slab which is fixed at ends. So at a radius r from the center of the slab, the expressions for mr and m theta are as follows. Mr equal to 1 by 16 w into r square minus 3r square, and m theta equal to 1 by 16 w r square minus small r square. You can refer in the figure which is drawn below this, and at the center small r will be equal to 0. mr will be equal to m theta will be equal to plus w r square by 16, and at the edges when small r equal to capital R, mr equal to minus 2w by 16 into r square. Please remember the negative sign is only due to the moment is at the support. No need for considering the negative sign for design. And here at the edges m theta will is equal to 0. You can see from the m theta diagram, m theta equal to 0. There is no positive m theta at the support, and the maximum shear force equal to W into R. So now we can move on to the problem. I will read out the question number 2. Design a circular slab fixed at the edges and carrying a UDL of 4 kN per meter square. Diameter is 6 meter and the floor finish 1 kN per meter square. Use M20 grade of concrete and Fe 415 grade of steel. For this problem, in mind I have drawn a sketch of the same. A circular slab which is fixed at both ends, which is having a diameter of 6 meter. That is inner diameter 6 meter. I have marked 3 meter from the center to the support, to the face of the support on both sides, and 230 is the support width. And now we can move on to the step number 1. First step is same as in the simply supported circular slab itself. So design constants FCK, Fi, Ru. Please refer the equation for finding out Ru from the previous example. From the example, Ru equal to 2.759 and mu limit equal to 2.76 into BD square, which is already familiar to you. And step number 2, it is dimensioning. Here we have L by D ratio for the circular slab is equal to 4 by 3 into L by D ratio of normal conventional one-way slab multiplied by 1.68. Here we have a clear span of 6 meter, effective span of 6.23 meter. To start with, we are considering effective span as 6.23. L by D ratio equal to 45. Therefore, D provided is 150, capital D is 180 mm. And now next is we have to find out the effective span. Clear span plus effective depth or center to center distance between the supports. So L effective equal to 6.15, the lesser of these two. From this, R equal to 6.15 by 2, that is 3.075. And next is step number 3, load calculation. So whatever loads are there, please write down all those loads and just find out the total load, and now then the factored load. Next is we have to find out the bending moment and shear force at the center of the slab as well as at the edges of the slab, both for mr as well as m theta. First we can find out at the center of the slab. So at the center of the slab, at mr equal to m theta equal to wr square by 16. Please refer the figure 8.42 kilonewton meter, and at the support m theta will be equal to 0 and mr will be equal to minus 2 by 16 w into r square. Please remember that negative sign shows that this moment is happening at the support. That's why it is negative. No need to consider this negative sign at the calculation part. So MR equal to 16.87 kilonewton meter. And we have to find out the maximum shear force, W into R. That's it. And just write down all these things by marking in a diagram. And the point of Conrad flexure is R by root 3. That is the point where the bending moment changes its sign. That is R by root 3 equal to 1.77. Now next step number 4, we have to find out the D required, or we have to check for D required. The steps are very much similar to the previous steps. MR equal to M theta equal to MU equal to which is less than MU limit. Therefore the slab can be designed as a normal or a singly reinforced slab. And next is we have to find out the ASTs for both MR and M theta at the center as well as at the support. So at the center, MR and M theta, in order to find out this, we have to get the D average. So D top, D bottom, you have to find out the D average. And MR, M theta equal to, at the center equal to 8.42 kilonewton meter. And just substitute everything, find out AST minimum, a spacing of that, and provide Y8 at 230 mm center to center. So this reinforcement is the one which we have to place at the bottom. Please remember that we have to place at the bottom of the circular slab. Next step is we have to find out the design of steel for the support moment. Design of steel for MR. We all know that MR is having some sort of negative moment at the support. So this reinforcement we need to show in the top. So we have to find out the negative MR. Here we don't have to consider rings and all. So we just give the D which we already obtained. That is 150 mm. So MR equal to 16.87. Support, since it is support, here we have minus 16.87, but we have to consider only 16.87. And we just found out the AST Y8 at 160 mm center to center at the support. And the next thing is you have to check for shear. Shear force is maximum or minimum at the support, right? So the maximum shear force will be equal to 43.8 PU by BD. D, the support D 150 mm, and you just find out the AST. AST is we have provided at the support, that is top reinforcement 8 at 160 mm. So we have found out the PT, tau V, tau C. Tau V should be less than tau C, hence it is safe. And now step number 7, that is the last step. We have to check for the development length. So LD should be less than or equal to M1 by V plus L naught. Here we have to consider 1.3 times M1 by V, since it is a circular slab. So the same step as in the previous problem, here we have to take D AST provided, since it is the AST which we need to provide, pi by 4 into D square into 1000 divided by 230. That is the AST provided. That is the main reinforcement which we have to provide. Then the support span reinforcement which we need to provide. So 47 times diameter. So diameter should be less than 10 mm. So we have already provided 8 mm diameter bars which is less than 10 mm. Therefore it is safe. And see here the detailing part. Both the top plan as well as the bottom plan is shown here. Bottom plan means our bottom reinforcement. Bottom reinforcement is the reinforcement which we are providing at the center of the circular slab. So the bottom reinforcement should be provided in the form of mesh. See that? These are provided in the form of mesh. The same we have marked at the elevation also 8 at 230. That is the bottom reinforcement in the form of mesh. And in the bottom itself, in bottom reinforcement we are just providing The bottom reinforcement is that 3 meter, 0.23 is the support width, and here we just see the top reinforcement. So top reinforcement is the negative reinforcement, a negative MR at the support. There we require 8 at 160 mm bars. So 8 at 160 mm is the one which we are providing at the top, 8 at 160. And at the same time, AST for M theta at the support is equal to 0, since this moment at M theta at the support is 0. Even though the positive moment is equal to 0, we have to provide at least a single ring at this. So we are providing one ring of 8 mm diameter at the edge of the slab, at the support. At the edge of the slab, we are just providing a single ring. So that ring is shown here. A single ring is provided, and that is how detailing of a slab, circular slab with a fixed support is being done. So this is the thing. So please do it, and for any clarification, please contact me. Thank you.